Yeah, good afternoon and welcome to the third week of facilitations for the course Physics 407 Solid State Physics 2. So last week we were almost getting to the end of the topic we have started treating the last 3 weeks, which is dielectric properties of solid. So this week we try as much as possible to complete the aspect and give a brief introduction to what we are going to discuss next week. So, if you have watched the videos of the last two classes, if you have any questions, you are free to ask me before we continue from where we stopped last week. Any questions? Okay. In the absence of no questions, so last week we were able to establish this equation 125, which we call Clausius equation, which expresses the relationship between the dielectric constant and the atomic polarizability. So we can calculate the electric constants of various materials from the polarizability using the formula Clausius equation. This equation holds fairly accurately for non-polar substance. Take note of that word. It produces correct result for non-polar substance but fail completely in pure polar liquid or solids. So the total polarizability of an atom can be separated into three parts. One, electronics, ionic, and orientational. So the electronic contribution arises from the formation of electronic shells about a nucleus, and the ionic or atomic configurations comes from the displacement and the formation of charged ion with respect to other ions. So the orientation or dipolar polarizability arises when the substance is built up of molecules. So possessing a permanent electric dipole moment, which may be more or less free to change orientation in an applied electric field. So in generally, we can write it as alpha is equal to alpha plus the three contribution, the dipolar, the ionic, and the electronics. So is the sum of the dipolar, this polarizability. So the electronic contribution is present in any type of substance, but the presence of other two terms depends on the material under consideration. So that is what we are trying to say about polarizability. Now, these are a few questions you are expected to answer yourself by using the note. You are expected to be able to define electric susceptibility and also polarizability. All these definitions have been stated in the note. So if you go through the note, you should be able to extract the definition from the note. Also, you are expected to explain the relevance of Clausius equation to material science. So, like we said, if you have Clausius equation, you can use it to derive dielectric constants of material, which is very good and important in the materials industry for production of materials for industrial applications. So, we move to the next thing, which is called dipole relaxation and dielectric losses. So if you have any question, you can ask me at this point before I proceed further. Okay, fine. Dipole relaxation time is the time interval characterizing the restoration of a disturbed system to its equilibrium configuration. So the relaxation frequency is defined as the reciprocal of relaxation time. So the orientational contribution to the dielectric constant is a major cause to the difference between the low frequency dielectric constant and the high frequency dielectric constant. So the orientational relaxation frequencies are strongly dependent on temperature and frequency. As so we now have this, which is equals to alpha naught over 1 plus high omega tau. So tau is known as thereby relaxation time, and alpha naught is static orientational probability, while omega is the angular frequency. Now let's consider, he said in liquid, relaxation time for a molecule of radius A can be expressed as this. So if you want to determine this, especially in a liquid, you have this, but in the solid, it varies. So in conclusion, we have reviewed the dielectric properties of solid in capacitors. We have seen the generation of local electric field. polarization and depolarization fields. So we also define dielectric constant and polarizability so as we also define susceptibility. Now, in summary, what we have discussed so far in the last 3 weeks, solid material can be divided into two distinct groups on the basis of their behavior under the influence of external electric fields. So we can have them as conductors or insulators. At times, dielectric that refers to insulators. So we can also have the dipole moment P is the vector along the axis of the dipole, pointing in direction of negative Q to positive Q, having a magnitude of QD. So depolarization P is defined as the dipole moment P per unit volume average over the volume of a cell. So the total dipole moment is defined by this. So these are things that we extracted from what we have discussed so far. Then depolarization charges on the outer surface of a specimen produce the depolarization field. So the depolarization field is opposite to polarization. When you have polarization, the opposite is what? Depolarization. So the local electric field at any atom of the dielectric may be written as this. This we have established this in the first week of the lecture by having this expression, and you can also write it more robust in this format. Now, for specimen in the shape of ellipsoid, oriented with one of the principal axes parallel to the applied field, it can be shown that the depolarization field will be parallel to the applied field and E will be negative MPD. So the constant N is known as depolarization factor. We established this also when we consider it along X, Y, and Z. So the dielectric constant epsilon has been defined for an isotropic or cubic medium relative to vacuum as epsilon is equals to d, which is displacement of electric field, and this can also be written as 1 plus p, which is polarization, all over epsilon naught e, and which is equals to 1 plus psi. Psi is now the electric susceptibility. So this susceptibility is related to dielectric constant by this expression. Susceptibility is equals to this, which is equals to epsilon minus 1. So if the field is not too large, the strength of the induced dipole moment in an atom I is proportional to local electric field acting on the dielectric. So what this is trying to tell us is that Pi is equal to alpha I EI log, where alpha I is polarizability and Pi is the dipole moment of atom I. Also, you have the polarization of a crystals may be expressed, the polarization of a crystal may be expressed approximately as the product of the polarizability of the atom times the local electric field, which is this expression, and at the end of the day, we have cross-Timothy equations derived from those concepts. So this is more or less like the summary of what we have done so far. Now there are some questions here which you are expected to solve. There are about five of them. They are simple questions. So you need to solve them. Try to lay your hands on them. Try them. If you have any issue, then you get back to me, then I'll put it through. But first, try it. The first question here says that two parallel plates have equal and opposite charges. When the space between the plates is evacuated, the electric field is 1.2 times 10 to the power of 5 volts per meter, and the electric field within the dielectric is 2 times 10 to the power of 5 volts per meter. Calculate the induced charge density on the surface of the dielectric. There is an expression that relates this. When you have induced electric field and induced dielectric and dielectric that is not induced by electric field. We have the equations. I think in the first week I expressed this. So that is what you are expected to use to solve this problem. Also, a parallel plate air capacitor is made up of 0.2 meters square thin plates and 1 centimeter apart, the distance that separates them. So it is connected to 50-volt battery. What is the charge on each plate? So this is more or less like trying to compute the charge when you have the electromotive force, which is the source of the cells. Then you have the distance. There is a kinetic equation between these that you can use to solve this problem. The plate of a parallel plate capacitor are 2 millimeters apart and 5 meters squared in area. So the plates are in vacuum. So a potential difference of 2000 volts is applied across the capacitor. Calculate the magnitude of the electric field between the plates. The fourth question there says that find the frequencies dependence of the electronic polarizability of an electron having the resonant frequency, this treating the system as a simple harmonic oscillator. And the last question there says that calculate the individual dipole moment P of a molecule of carbon tetrachloride given the following data. So a reference textbook that is very good for this area is what we know as Introduction to Solid State Physics, written by Charles Kittel. So any question? Any questions? Okay, in the absence of no questions, so next week we will start discussion on magnetism. So these are basically what we are going to be discussing next week. Magnetization, diamagnetization, paramagnetism, and ferromagnetism. So we discuss what magnetism is, then the type. After that, we look at Curie-Wern's law. Then we also look at spontaneous magnetization, then the domain theory of magnetism. We also look at the Bloch wall, domain dimension, and antiferromagnetism. Then we give series of materials, type of material that has most of these magnetic properties. And we round it up by looking at magnetic resonance, where we are going to be discussing nuclear magnetic resonance, ferromagnetic resonance, and antiferromagnetic resonance. So by so doing, we shall be moving close to the end of the class. So if you have any questions, you are free to ask me before next week. Any questions? Okay, in the absence of no questions, I think I have to stop the class for today till next week.